A database is just what the name implies, a base collection of data. The data is organized in some manner so that the information contained within the database can be easily retrieved. Some of the simple databases that you might be familiar with are things like phone books or Rolodexes. As data processing has become more sophisticated, so have methods for collecting, storing, and retrieving information. Databases have become the cornerstone for an overwhelming amount of the computing environment in existence. A database has the following properties. It is a representation of some aspect of the real world or a collection of data elements representing real-world information. A database is logical, coherent, and internally consistent. A database is designed, built, and populated with data for a specific purpose. Each data item is stored in a field. A combination of fields makes up a table. For example, each field in an employee table contains data about an individual employee. A database management system, or DBMS, is a collection of programs that enables users to create and maintain databases and control all access to them. The primary goal of a DBMS is to provide an environment that is both convenient and efficient for users to retrieve and store information. Managing information means taking care of it so that it works for us and is useful for the tasks we perform. By using a DBMS, the information we collect and add to its database is no longer subject to accidental disorganization. It becomes more accessible and integrated with the rest of our work. Managing information using a database allows us to become strategic users of the data we have. We often need to access and resort data for various uses. These may include creating mailing lists, writing management reports, generating lists of selected news stories, identifying various client needs. The processing power of a database allows it to manipulate the data it houses, so it can sort, match, link, aggregate, skip fields, calculate, or arrange. Because of the versatility of databases, we find them powering all sorts of projects. A database can be linked to a website that is capturing registered users, a client tracking application for social service organizations, a medical record system for a healthcare facility, your personal address book in your email client, a collection of word processed documents, or a system that issues airline reservations. There are a number of characteristics that distinguish the database approach from the file-based system or approach. This chapter describes the benefits and features of the database system. A database system is referred to as self-describing because it not only contains the database itself, but also metadata, which defines and describes the data and relationships between tables in the database. This information is used by the DBMS software or database users if needed. This separation of data and information about the data makes a database system totally different from the traditional file-based system in which the data definition is part of the application programs. In the file-based system, the structure of the data files is defined in the application programs, so if a user wants to change the structure of a file, all the programs that access that file might need to be changed as well. On the other hand, in the database approach, the data structure is stored in the system catalog and not in the programs. Therefore, one change is all that is needed to change the structure of a file. This insulation between the programs and data is called program data independence. A database supports multiple views of data. A view is a subset of the database, which is defined and dedicated for particular users of the system. Multiple users in the system might have different views of the system. Each view might contain only the data of interest to a user or a group of users. Current database systems are designed for multiple users. That is, they allow many users to access the same database at the same time. This access is achieved through features called concurrency control strategies. These strategies ensure that the data accessed are always correct and that data integrity is maintained. The design of modern multi-user database systems is a great improvement from those in the past, which restricted usage to one person at a time. In the database approach, ideally each data item is stored in only one place in the database. In some cases, data redundancy still exists to improve system performance, but such redundancy is controlled by application programming and kept to minimum by introducing as little redundancy as possible when designing the database. The integration of all the data for organization within a database system has many advantages. First, it allows for data sharing among employees and others who have access to the system. Second, it gives users the ability to generate more information from a given amount of data than would be possible without the integration. Database management systems must provide the ability to define and enforce certain constraints to ensure that users enter valid information and maintain data integrity. A database constraint is a restriction or rule that dictates what can be entered or edited in a table, such as a postal code using a certain format or adding a valid city in the city field. There are many types of database constraints. Data type, for example, determines the sort of data permitted in a field. For example, numbers only. Data uniqueness, such as the primary key, ensures that no duplicates are entered. Constraints can be simple, like field-based, or complex, like programming. Not all users of a database system will have the same accessing privileges. For example, one user might have read-only access, that is, the ability to read a file but not make changes, while another might have read and write privileges, which is the ability to both read and modify a file. For this reason, a database management system should provide a security subsystem to create and control different types of user accounts and restrict unauthorized access. Another advantage of a database management system is how it allows for data independence. In other words, the system data descriptions or data describing data, metadata, are separated from the application programs. This is possible because changes to the data structure are handled by the database management system and are not embedded in the program itself. A database management system must include concurrency control subsystems. This feature ensures that data remains consistent and valid during transaction processing, even if several users update the same information. By its very nature, a DBMS permits many users to have access to its database, either individually or simultaneously. It is not important for users to be aware of how and where the data they access is stored. Backup and recovery are methods that allow you to protect your data from loss. The database system provides a separate process from that of a network backup for backing up and recovering data. If a hard drive fails and the database stored on the hard drive is not accessible, the only way to recover the database is from a backup. If a computer system fails in the middle of a complex update process, the recovery subsystem is responsible for making sure that the database is restored. The so-called semantic modeling method nowadays is commonly used in database structure design. Semantic modeling is modeling data structures based on the meaning of these data. Different variants of the entity relationship diagrams are used as a tool for the semantic modeling. ER model-based diagrams have three main components: an entity, a relation, and attributes. An entity is a class of similar objects, information about which should be taken into account in the model. Each entity must have a name, expressed by a noun in the singular. Examples of entities can be such classes of objects as supplier, employee, or invoice. Each entity in the model is depicted in the form of a rectangle with the name. While determining the type of entity, it is necessary to be sure that each instance of an entity may be indistinguishable from any other instance of the same entity. Relation is presented in the form of a non-directional line connecting two entities or leading from the entity to itself. In the place of docking, an entity uses 3-point entry to the entity rectangle, if many instances of the entity may be used for this relation. Single-point entry if relation can or should participate in only one instance of the entity. Relation between entities ticket and passenger connects passengers and tickets. One side of the relation with a label for is a many-to-many relation, which allows to relate more than one ticket to a passenger, and each ticket must be linked to any passenger. Another side of the relation with a label have is a 0 or 1 relation, which shows that each ticket can belong to only one passenger, and the passenger is not obliged to have at least one ticket. Attribute of an entity is a detail or feature that is used for verification, identification, classification, numerical characteristics, or expressing status of the entity. Attribute names are recorded in the rectangle representing an entity under entity name. For instance, an entity human being may have such attributes as gender, year of birth, first name, etc. The relational data model was introduced by C.F. Codd in 1970. Currently, it is the most widely used data model. The relational model has provided the basis for research on the theory of data, relationship, constraint, numerous database design methodologies, the standard database access language called Structured Query Language or SQL, and almost all modern commercial database management systems. Furthermore, the relational data model describes the world as a collection of interrelated relations or tables. Now let's talk about the fundamental concepts in the relational data model. A relation, also known as a table or file, is a subset of the Cartesian product of a list of domains characterized by a name, and within a table, each row represents a group of related data values. A row or record is also known as a tuple. The columns in a table is a field and is also referred to as an attribute. You can also think of it this way. An attribute is used to define the record, and a record contains a set of attributes. The steps I'm about to mention outline the logic between a relation and its domains. Given n domains are denoted by d1, d2, up until dn, and R is a relation defined on these domains, then R has some or all elements of d1, xd2, x up until xdn. Now let's talk about tables. A database is composed of multiple tables, and each table holds the data. And then we talk about columns. A database stores pieces of information or facts in an organized way. Understanding how to use and get the most out of databases requires us to understand that method of organization. The principal storage units are called columns or fields or attributes. These house the basic components of data into which your content can be broken down. When deciding which fields to create, you need to think generically about your information. For example, drawing out the common components of the information that you will store in the database and avoiding the specifics that distinguish one item from another. And then we move to domains. A domain is the original set of atomic values used to model data. By atomic value, we mean that each value in the domain is indivisible as far as the relational model is concerned. For example, the domain of marital status has a set of possibilities: married, single, divorced. The domain of shift has the set of all possible days: Monday, Tuesday, Wednesday, etc. The domain of salary is the set of all floating point numbers greater than 0 and less than 200,000. The domain of first name is the set of character strings that represents names of people. In summary, a domain is a set of acceptable values that a column is allowed to contain. This is based on various properties and the data type for the column. We will discuss data types in another chapter. And now we move to records. Just as the content of any one document or item needs to be broken down into its constituent bits of data for storage in the fields, the link between them also needs to be available so that they can be reconstituted into their whole form. Records allow us to do this. Records contain fields that are related, such as a customer or an employee. As noted earlier, a tuple is another term used for record. Fields can hold a range of different sorts of data. This one has a record ID field. This is an ordinal number. Its data type is an integer. A pubdate field. This is displayed as day/month/year. Its data type is date. An author field. This is displayed as initial, surname. Its data type is text. And a title field text, free text, can be entered here. You can command the database to sift through its data and organize it in a particular way. For example, you can request that a selection of records be limited by date. That is, number 1, all before a given date. Number 2, all after a given date. Or number 3, all between two given dates. Similarly, you can choose to have records sorted by date. Because the field or record containing the data is set up as a date field, the database reads the information in the date field not just as numbers separated by slashes, but rather as dates that must be ordered according to a calendar system. Degree. The degree is the number of attributes in a table. Okay, now let's talk about the properties of a table. A table has a name that is distinct from all other tables in the database. There are no duplicate rows. Each row is distinct. Entries in columns are atomic. The table does not contain repeating groups or multi-valued attributes. Entries from columns are from the same domain based on their data type, including number, like numeric, integer, float, or small integer, character, string, date, logical, like true or false. Operations combining different data types are disallowed. Each attribute has a distinct name, and the sequence of columns is insignificant. The sequence of rows as well is insignificant. Now let's talk about the types of data models. High-level conceptual data models. High-level conceptual data models provide concepts for presenting data in ways that are close to the way people perceive data. A typical example is the entity relationship model, which uses main concepts like entities, attributes, and relationships. An entity represents a real-world object such as an employee or a project. The entity has attributes that represent properties such as an employee's name, address, and birth date. A relationship represents an association among entities. For example, an employee works on many projects. A relationship exists between the employee and each project. Record-based logical data models. Record-based logical data models provide concepts users can understand but are not too far away from the way data is stored in the computer. Three well-known data models of this type are relational data models, network data models, and hierarchical data models. The relational model represents data as relations or tables. For example, in the membership system at Science World, each membership has many members. The membership identifier, expiry date, and address information are fields in the membership. The members are individuals such as Mickey, Minnie, Mighty, Dor, Tom, Data modeling is the first step in the process of database design. This step is sometimes considered to be a high-level and abstract design phase, also referred to as conceptual design. The aim of this phase is to describe the data contained in the database, example, entities like students, lecturers, courses, subjects. The relationships between data items, example, students are supervised by lecturers, lecturers teach courses. The constraints on data, example, student number has exactly 8 digits. A subject has 4 or 6 units of credit only. In the second step, the data items, the relationships, and the constraints are all expressed using the concepts provided by the high-level data model. Because these concepts do not include the implementation details, the result of the data modeling process is a semi-formal representation of the database structure. This result is quite easy to understand, so it is used as a reference to make sure that all the user's requirements are met. The third step is database design. During this step, we might have two sub-steps, one called database logical design, which defines a database in a data model of a specific DBMS, and another called database physical design, which defines the internal database storage structure, file organization, or indexing techniques. These two sub-steps are database implementation and operations/user interfaces building steps. In the database design phases, data are represented using a certain data model. The data model is a collection of concepts or notations for describing data, data relationships, data semantics, and data constraints. Most data models also include a set of basic operations for manipulating data in the database. In this section, we will look at the database design process in terms of specificity. Just as any design starts at a high level and proceeds to an ever-increasing level of detail, so does database design. For example, when building a home, you start with how many bedrooms and bathrooms the home will have, whether it will be on one level or multiple levels, etc. The next step is to get an architect to design the home from a more structured perspective. This level gets more detailed with respect to actual room sizes, how the home will be wired, where the plumbing fixtures will be placed, etc. The last step is to hire a contractor to build the home. That's looking at the design from a high level of abstraction to an increasing level of detail. The database design is very much like that. It starts with users identifying the business rules, then the database designers and analysts create the database design, and then the database administrator implements the design using a DBMS. The following subsections summarize the models in order of decreasing level of abstraction. External models represent the user's view of the database and contain multiple different external views that are closely related to the real world as perceived by each user. Conceptual models provide flexible data structuring capabilities and present a community view. The logical structure of the entire database contain data stored in the database show relationships among data including constraints, semantic information such as business rules, security, and integrity information. Consider a database as a collection of entities or objects of various kinds that are the basis for identification and high-level description of main data objects. They avoid details which are database independent regardless of the database you will be using. And now let's talk about internal models. The three best-known models of this kind are the relational data model, the network data model, and the hierarchical data model. These internal models consider a database as a collection of fixed-size records that are closer to the physical level or file structure, a representation of the database as seen by the DBMS. It also requires the designer to match the conceptual model's characteristics and constraints to those of the selected implementation model. It also involves mapping the entities in the conceptual model to the tables in the relational model. Physical models are the physical representation of the database, and they have the lowest level of abstractions and are how the data is stored. They also deal with runtime performance, storage utilization and compression, file organization, and access methods. Data encryption are the physical level, managed by the operating system or OS. It also provides concepts that describe the details of how data are stored in the computer's memory. Data abstraction layer. In a pictorial view, you can see how the different models work together. Let's look at this from the highest level, the external model. The external model is the end user's view of the data. Typically, a database is an enterprise system that serves the needs of multiple departments. However, one department is not interested in seeing other departments' data. Example, the human resources or HR department does not care to view the sales department's data. Therefore, one user view will differ from another. The external model requires that the designer subdivide a set of requirements and constraints into functional modules that can be examined within the framework of their external models. Example, human resources versus sales. As a data designer, you need to understand all the data so that you can build an enterprise-wide database. Based on the needs of various departments, the conceptual model is the first model created. At this stage, the conceptual model is independent of both software and hardware. It does not depend on the DBMS software used to implement the model. It does not depend on the hardware used in the implementation of the model. Changes in either hardware or DBMS software have no effect on the database design at the conceptual level. Once a DBMS is selected, you can then implement it. This is the internal model. Here, you create all the tables, constraints, keys, rules, etc. This is often referred to as the logical design. The physical model is simply the way the data is stored on the disk. Each database vendor has its own way of storing the data. Now let's talk about schemas. A schema is an overall description of a database, and it is usually represented by the Entity Relationship Diagram, or ERD. There are many subschemas that represent external models, and thus display external views of the data. Following are a list of items to consider during the design process of a database. Let's talk about external schemas. First, you have your multiple subschemas. These display multiple external views of the data. Then you have your conceptual schema. There is only one. This schema includes data items, relationships, and constraints, all represented in an ERD. Then you have your physical schema. There is only one. Logical and physical data independence. Data independence refers to the immunity of user applications to changes made in the definition and organization of data. Data abstractions expose only those items that are important or pertinent to the user. Complexity is hidden from the database user. Data independence and operation independence together form the feature of data abstraction. There are two types of data independence, logical and physical. Let's first talk about logical data independence. A logical schema is a conceptual design of the database done on paper or a whiteboard, much like architectural drawings for a house. The ability to change the logical schema without changing the external schema or user view is called logical data independence. For example, the addition or removal of new entities, attributes, or relationships to this conceptual schema should be possible without having to change existing external schemas or rewrite existing application programs. In other words, changes to the logical schema, example alterations to the structure of the database like adding a column or other tables, should not affect the function of the application, like external views. Physical data independence refers to the immunity of the internal model to changes in the physical model. The logical schema stays unchanged even though changes are made to file organization or storage structures, storage devices, or indexing strategy. Physical data independence deals with hiding Relational algebra is procedural query language, which takes relation as input and generate relation as output. Relational algebra mainly provides theoretical foundation for relational databases and SQL. Now let's talk about operators in relational algebra. We'll start with projection, which is represented by the pi sign. Projection is used to project required column data from a relation. Example: R, A, B, C, 1, 2, 4, 2, 2, 3, 3, 2, 3, 4, 3, 4, pi, BC. BC, 2, 4, 2, 3, 3, 4. Note, by default, projection removes duplicate data. Now let's talk about selection, which is represented by the sigma sign. Selection is used to select required tuples of the relations. For the following relation, sigma c greater than 3r will select the tuples which have c more than 3. Note, selection operator only selects the required tuples but does not display them. For displaying, data projection operator is used. For the following selected tuples, to display we need to use projection also. Pi sigma c greater than 3r will show following tuples: A, B, C, 1, 2, 4, 4, 3, 4. Now we move to union, represented by the letter U. Union operation in relational algebra is same as union operation in set theory. Only constraint is for union of two relation, both relation must have same set of attributes. And now for set difference, which is represented by the minus sign. Set difference in relational algebra is same set difference operation as in set theory, with the constraint that both relations should have same set of attributes. Now let's talk about rename, which is represented by the raw sign. Rename is a unary operation used for renaming attributes of a relation. Raw A over BR will rename the attribute B of relation by A. And now for cross product, represented by the letter X. Cross product between two relations, let's say A and B, so cross product between A x B will result all the attributes of A followed by each attribute of B. Each record of A will pair with every record of B. The following is the example. Here you have two sets, A and B, A representing name, age, sex, and B with ID and course. So under name you have Ram, Sana, Kim, age 14, 15, 20, sex, male, female, male. And then you have ID 1 and 2, and course DS and DBMS. When you go AXB, it becomes name, age, sex, ID, course, and you have RAM 14, M1 DS, RAM 14, M2 DBMS, Sana 15 F1 DS, Sana 15 F2 DBMS, Kim 20 M1 DS, Kim 20 M2 DBMS. Note, if A has n tuples and B has m tuples, then A x B will have n times m tuples. And now we move to natural join, represented by the bow tie sign. Natural join is a binary operator. Natural join between two or more relations will result in a set of all combinations of tuples where they have equal common attributes. Let's see the following example. Here you have two sets, one EMP signifying employee and another DEP signifying department. Under employee you have name, ID, department name. Under DEP you have department name and manager. Under name you have A, B, C, D, ID 120, 125, 110, 111. Department name, IT, HR, sale, IT. Under DEP's department name you have sale, prod, and IT. And under manager you have YZA. So employee natural join department becomes name, ID, department name, manager with the following details. ACD 120, 110, 111, IT, sale, IT, AYA. And then you have conditional join. Conditional join works similar to natural join. In natural join, by default, condition is equal between common attribute, while in conditional join, we can specify any condition, such as greater than, less than, not equal. Let's see the following example. You have two sets, R and S. Under R, you have ID, sex, and marks. Same goes with set S. Under ID, you have 1, 2, 3. Under sex, FFF. Under marks, 45, 55, and 60. Under S, ID 10, 11, 12. Sex, MMM. Marks 20, 22, 59. Join between R and S with condition R marks are greater than or equal to S marks. You will have the following set. RID, R sex, R marks. SID, S sex, S marks. And then you have the following data. Under RID 1122333, under R sex FFFFFFF, under R marks 45, 45, 55, 55, 60, 60, 60, under SID 10, 11, 10, 11, 10, 11, 12. Under S sex you have all MMM, and under S marks you have 20, 22, 20, 22, 20, 22, 59. Relational algebra received little attention outside of pure mathematics until the publication of E.F. Codd's relational model of data in 1970. Codd proposed such an algebra as a basis for database query languages. 5 primitive operators of Codd's algebra are the selection, the projection, the Cartesian product, also called the cross product or cross join, the set union, and the set difference. And finally, let's talk about set operators. The relational algebra uses set union, set difference, and Cartesian product from set theory, but adds additional constraints to these operators. For set union and set difference, the two relations involved must be union compatible. That is, the two relations must have the same set of attributes. Because set intersection is defined in terms of set union and set difference, the two relations involved in set intersection must also be union compatible. For the Cartesian product to be defined, the two relations involved must have disjoint headers. That is, they must not have a common attribute name. In addition, the Cartesian product is defined differently from the one in set theory, in the sense that tuples are considered to be shallow for the purposes of the operation. That is, the Cartesian product of a set of n tuples with a set of m tuples yields a set of flattened n plus m tuples, whereas basic set theory would have prescribed a set of 2 tuples, each containing an n tuple and an m tuple. More formally, R times S is defined as follows. Display style R \, times S : equals \ R underscore 1, R underscore 2, dots, R underscore N, S underscore 1, S underscore 2, dots, S underscore M, R underscore 1, R underscore 2, dots, R underscore N, \ in R, S underscore 1, S underscore 2, dots, S underscore M in S, R \, times S : equals r_1, r_2, dots, r_n, s_1, s_2, dots, s_m, r_1, r_2, dots, r_n, in r, s_1, s_2, dots, s_m in s. The cardinality of the Cartesian product is the product of the cardinalities of its factors, that is, Structured Query Language, or SQL, is a database language designed for managing data held in a relational database management system. SQL was initially developed by IBM in the early 1970s, date 1986. The initial version, called SQL, or Structured English Query Language, was designed to manipulate and retrieve data stored in IBM's quasi-relational database management system, System R. Then in the late 1970s, Relational Software Incorporated, which is now Oracle Corporation, introduced the first commercially available implementation of SQL, Oracle V2 for VAX computers. Many of the currently available relational DBMSs, such as Oracle Database, Microsoft SQL Server, MySQL, IBM DB2, IBM Informix, and Microsoft Access, use SQL. In a DBMS, the SQL database language is used to create the database and table structures, perform basic data management chores like add, delete, and modify, and perform complex queries to transform raw data into useful information. In this chapter, we will focus on using SQL to create the database and table structures, mainly using SQL as a data definition language, or DDL. The optional column constraints are null, not null, unique, primary key, and default, used to initialize a value for a new record. The column constraint null indicates that null values are allowed, which means that a row can be created without a value for this column. The column constraint not null indicates that a value must be supplied when a new row is created. Table constraints are identified by the constraint keyword and can be used to implement various constraints described in the following. Identity constraint. We can use the optional column constraint identity to provide a unique incremental value for that column. Identity columns are often used with the primary key constraints to serve as the unique row identifier for the table. The identity property can be assigned to a column with a tiny int, small int, decimal, or numeric data type. This constraint generates sequential numbers, does not enforce entity integrity, only one column can have the identity property, must be defined as an integer, numeric, or decimal data type, cannot update a column with the identity property, cannot contain null values, cannot bind defaults and default constraints to the column. For identity, seed increment. Seed is the initial value of the identity column. Increment is the value to add to the last increment column. Unique constraint. The unique constraint prevents duplicate values from being entered into a column. Both PK and unique constraints are used to enforce entity integrity. Multiple unique constraints can be defined for a table. When a unique constraint is added to an existing table, the existing data is always validated. A unique constraint can be placed on columns that accept nulls. Only one row can be null. A unique constraint automatically creates a unique index on the selected column. Foreign key constraint. The foreign key, or FK constraint, defines a column or a combination of columns whose values match the primary key, or PK, of another table. Values in an FK are automatically updated when the pk values in the associated table are updated or changed. Fk constraints must reference pk or the unique constraint of another table. The number of columns for Fk must be same as pk or unique constraint. If the with no check option is used, the Fk constraint will not validate existing data in a table. No index is created on the columns that participate in an Fk constraint. Now let's talk about check constraint. The check constraint restricts values that can be entered into a table. And let's talk about default constraint. The default constraint is used to supply a value that is automatically added for a column if the user does not supply one. A column can have only one default. The default constraint cannot be used on columns with a timestamp data type or identity property. Default constraints are automatically bound to a column when they are created. The SQL data manipulation language, or DML, is used to query and modify database data. In this chapter, we will describe how to use the select, insert, update, and delete SQL DML command statements defined as follows. Select, to query data in the database. Insert, to insert data into a table. Update, to update data in a table. Delete, to delete data from a table. In the SQL DML statement, each clause in a statement should begin on a new line. The beginning of each clause should line up with the beginning of other clauses. If a clause has several parts, they should appear on separate lines and be indented under the start of the clause to show the relationship. Uppercase letters are used to represent reserved words. Lowercase letters are used to represent user-defined words. The select statement or command allows the user to extract data from tables based on specific criteria. It is processed according to the following sequence: select distinct items, from tables, where predicate, group by fields, order by fields. Sometimes you might want to focus on a portion of the publishers table, such as only publishers that are in Vancouver. In this situation, you would use the select statement with the where criterion, that is, where city equals Vancouver. These first two examples illustrate how to limit record selection with the where criterion using between. Each of these examples give the same results for store items with between 20 and 50 items in stock. The like keyword selects rows containing fields that match specific portions of character strings. Like is used with car, varchar, text, datetime, and small datetime data. A wildcard allows the user to match fields that contain certain letters. For example, the wildcard province equals n% would give all provinces that start with the letter n. The having clause can be used to restrict rows. It is similar to the where condition, except having can include the aggregate function. The where cannot do this. The having clause behaves like the where clause, but is applicable to groups. In this example, we use the having clause to exclude the groups with the province BC. The insert statement adds rows to a table. In addition, insert specifies the table or view that data will be inserted into. Column list lists columns that will be affected by the insert. If a column is omitted, each value must be provided. If you are including columns, they can be listed in any order. Values specifies the data that you want to insert into the table. Values is required. columns with the identity property should not be explicitly listed in the column list or values clause. When inserting rows with the insert statement, these rules apply. Inserting an empty string into a varchar or text column inserts a single space. All char columns are right-padded to the defined length. All trailing spaces are removed from data inserted into varchar columns, except in strings that contain only spaces. These strings are truncated to a single space. If an insert statement violates a constraint, default or rule, or if it is in the wrong data type, the statement fails and SQL Server displays an error message. When you specify values for only some of the columns in the column list, one of three things can happen to the columns that have no values. A default value is entered if the column has a default constraint. If a default is bound to the column, or if a default is bound to the underlying user-defined data type. Null is entered if the column allows nulls and no default value exists for the column. An error message is displayed and the row is rejected if the column is defined as not null and no default exists. By default, data cannot be inserted directly into an identity column. However, if a row is accidentally deleted or there are gaps in the identity column values, you can insert a row and specify the identity column value. There are many built-in functions in SQL Server, such as aggregate, returns summary values, conversion, transforms one data type to another, date, displays information about dates and times, mathematical, performs operations on numeric data, string, performs operations on character strings, binary data, or expressions, system, returns a special piece of information from the database, text and image, performs operations on text and image data. Aggregate functions perform a calculation on a set of values and return a single or summary value. As for function descriptions, AVG returns the average of all the values or only the distinct values in the expression. Count returns the number of non-null values in the expression. When distinct is specified, count finds the number of unique non-null values. Count asterisk returns the number of rows. Count asterisk takes no parameters and cannot be used with distinct. Max returns the maximum value in the expression. Max can be used with numeric, character, and date-time columns, but not with bit columns. With character columns, max finds the highest value in the collating sequence. Max ignores any null values. Min returns the minimum value in the expression. Min can be used with numeric, character, and date-time columns, but not with bit columns. With character columns, min finds the value that is lowest in the sort sequence. Min ignores any null values. One thing that you will most certainly run into at one point or another when working with Microsoft SQL Server or any other relational database management system or RDBMS is blocked processes caused by locks on database objects. But what are database locks and why can they sometimes cause one process to block another? Locking is an integral part of any successful processing of transactions in any good RDBMS. The reason for this is the need for data integrity within the system. One of the important ways RDBMS keeps the integrity of the data stored is by making every transaction pass the ACID test, which means it meets the following criteria. Atomic. The transaction performs in an all or nothing fashion. Consistent. Transactions are processed in a uniform manner. Isolated. Transactions are properly isolated until they are finished. Durable. The RDBMS will maintain a record of uncompleted transactions in the event of recovery during a failure. The isolation part of the acid test is addressed by locking objects, in most cases one or more rows of data, until the associated transactions are completed. The locking of objects stops all other processes from being able to change these objects until the lock is removed. Blocking is the logical outcome of locks being issued against various objects in a database. If a request is made against an object which has a lock issued against it, then the request is delayed until the lock is removed. The delaying or stopping of a transaction is referred as a block. An example of this would be if request A is attempting to insert a row in table T. Subsequently, before request A completes, request B submits an update on table T. If the row affected by request A is also affected by request B, then a block is encountered. Because the row affected by request A has an exclusive lock issued against it for the duration of the transaction. There will always be some level of blocking in an SQL Server database. This is the natural outcome of the goal of 100% data integrity and the resulting need for locks. High levels of blocking or blocks that are not quickly resolved can become a major concern. Blocking can impact a company's ability to keep its data current, and it can also affect the end users of that data, such as clients coming to its website. One of the most common symptoms of excessive blocking is high SQL Server wait counts, which in turn can cause slow response times to requests made on a database. There are a number of ways to locate blocking issues in SQL Server, and in turn, the system process IDs, SPIDs, involved in blocking. If you have the correct SQL Server permissions, here are two of the easiest ways to find them using SQL Server Management Studio. To find blocks using this method, open SQL Server Management Studio and connect to the SQL Server instance you wish to monitor. After you have connected, right-click on the instance name and select Activity Monitor from the menu. SQL Server Activity Monitor 1. Once Activity Monitor has loaded, expand the Processes section. Any processes which are currently in a blocked state will display the SPID of the processes blocking it in the Block By column. In the example as follows, we see the SPID 55 is being blocked by SPID 54. SQL Server Activity Monitor 2. SQL Server System Stored Procedure SP_who2. To find blocks using this method, open SQL Server Management Studio and connect to the SQL Server instance you want to run the stored procedure on. After you have connected, right-click on the instance name and select New Query from the menu. SQL Server SP_who1. Once the new SQL Server query window opens, type the following TSQL statements in the window and execute them. Use master, go, exec sp_who2, go. A list of processes will be displayed, and any processes which are currently in a blocked state will display the SPID of the processes blocking them in the Block By column. In the following example, we see that SPID 55 is being blocked by SPID 54. SQL Server SP_who2. Understanding which queries and processes are causing blocks is important in helping make sure your website is running smoothly and providing the best experience for its users. Blocked processes caused by locks on database objects are a common issue. Locking ensures the integrity of data stored within databases by forcing each executed SQL Server transaction to pass the ACID test, which considers that every transaction must meet the following requirements: atomicity, A transaction must be either fully completed when executed or it will not execute at all. Consistency. Transactions must create a new state of data that is valid, or if any failure occurs, it must return all data to the state that was actual before the transaction is executed or started. Isolation. A transaction that is in process of execution and is not committed yet must be isolated from all other transactions. Durability. Committed data must be saved in a way that will maintain data in correct state if a transaction does not complete in the event of a failure and restart of the system. As part of the acid test, isolation is carried out by locking effects objects, and as such, isolation can affect one or more data rows until the SQL Server transaction that is executed against that object is committed. This means, in practice, that by locking the object, SQL Server will prevent any other process from making any change against the data in that object until the lock is removed, either by committing the change or rolling it back. Imposing the lock over an object will cause any other process that imposes a request against the locked object to wait until the lock is removed, which will delay execution of that process. The state when a transaction is waiting for the lock to be removed or stopped is what is known as a block. SQL Server is designed to work this way, and as such, blocks are not inherently problematic. Therefore, only when a high level of blocks is detected on SQL Server, or in a case in which blocks occurs that require excessive amount of time to be resolved, should it be treated as a potential issue. A practical example of SQL Server blocking is when transaction number 1 is trying to update data in table A, and while transaction 1 is still running and is not completed, transaction 2 tries to place a new lock on table A. If the row that should be deleted is also the row that will be updated by transaction 2, then transaction 2 will encounter a block. This is because transaction 1 has an exclusive lock imposed on the table while the transaction is running. So, how do we identify instances of SQL Server blocking? There are a couple of ways to do this in SQL Server. First is using Activity Monitor, and second is using SQL Server DMVs. Activity Monitor is an SQL Server Management Studio tool that enables users to see details of existing SQL Server connections, and it can be used to show information about the open processes and locks on SQL Server resources. To open Activity Monitor in SQL Server Management Studio, right-click the SQL Server name in Object Explorer and click Activity Monitor. Expand the processes and locate the process that is waiting. Once the process is located, take a look at the Blocked By column to find the process ID that has caused the blocking. Now, when the process that is causing the blocking is identified, it has to be located in the same processes page. Now, when the information about the process that is causing the blocking is found, the user might opt to kill that process or to allow it to run until it completes. To kill the process, right-click on it and select Kill Process. The Dynamic Management View, sys.dm exec request, is used for identifying the SQL Server blocks. It can be used to list currently active blocks by executing the following query. Use master, go, select session ID, blocking session ID, wait time, wait type, last wait type, wait resource, transaction isolated, on level, lock timeout, from sys.dm exec request, where blocking session ID, less than greater than 0, go. In the results, it can be seen which process is blocked, session ID, what process is blocking, blocking session ID, what wait type is involved, and what the wait time of that blocking is, as well as the resources involved. To terminate the blocking session, ID 74 in this case, use the kill command, kill 74, go. Here's a quick tip. Take care when killing a process and make sure that there is a complete understanding of what that process is doing and why it is causing blocks. When a transaction is killed, all data changes made by that process to be rolled back into a previous state. But these native SQL Server methods can be used only for detecting and identifying active blocks. In many situations, when a block is detected and identified, it is important to know whether this constitutes normal behavior and whether it occurs rarely or only once. Without such information, it is not possible to perform required troubleshooting, simply because no historical data about blocks are available, such as blocking frequency and the extent of blocking. This is why a third-party performance monitoring tool like Apex SQL Monitor can be helpful. Apex SQL Monitor is a performance monitoring tool that can track weight statistics on the individual query level, store data in a central repository database to ensure easy access to historical information. To use the Apex SQL Monitor to identify the SQL Server blocks, select the SQL Server instance in the left pane that you have to troubleshoot. Go to the Query Weights tab by selecting the charts in the main menu. Now select the Query Weights tab and check the Block Queries radio button. If there are any blocked queries, they will be listed in the grid and displayed in the chart. By expanding the specific query on the plus sign at the beginning of the row, details about that query block will be displayed. Here, the most important information is related to the blockers section. Information about SPID number of the process that is causing the block, and resources involved in this block, wait resource. For better understanding of how to decipher the resource, please refer to the Microsoft article, INF, Understanding and Resolving SQL Server Blocking Problems. Every block is actually a situation when one process is waiting on another process to release the lock, so SQL Server will register that wait using the LCK_M_XXX wait type. Depending on what the blocked query is waiting for, this query wait will be displayed. By mouse clicking on the wait type name, helper information about the wait type and advice on resolution with additional links to resources about that wait type will be displayed. So now it is easy for the user to get detailed info about not only the current blocking, but also about all blocks that occurred in the monitored SQL server. Users can now easily analyze how often the specific query has been blocked and by what processes. To check the history of the blocks for that particular query, access the History tab. As it can be seen from the image, this query has been blocked only once during the day by process SPID 74. But if we check the other blocked queries, it can be seen that it is always the SPID 74 process that is involved in all blocks. This seems like actionable information that could be further investigated. In addition, it is good advice to check the previous days for blocks that occurred in order to better understand when, why, and how it occurred. To do that, select the previous day, for example, from the date picker in the Query Weights tab. The SPID 72 was blocked 4 times during the previous day, and after taking a closer look at the details, it can be seen that SPID 72 was itself blocked by SPID 74. Based on this, there is reliable evidence that it is not just a rare case of blocking, but that blocking occurs regularly and is caused by SPID 74. Therefore, SPID 74 and the query behind that process ID is causing the blocks, and the SPID 74 query must be investigated more closely. In order to track the blocked query or Data aggregation is any process in which information is gathered and expressed in a summary form for purposes such as statistical analysis. A common aggregation purpose is to get more information about particular groups based on specific variables such as age, profession, or income. Sometimes a class type really represents a collection of individual components. Although this pattern can be modeled by an ordinary association, its meaning becomes much clearer if we use the UML notation for an aggregation. Example: a small business needs to keep track of its computer systems. They want to record information such as model and serial number for each system and its components. A very naive way to do this would be to put all of the information into a single class type. You should recognize that this class contains a set of repeated attributes with all of the problems of the phone book pattern. You could fix it as we show here. Here we have the incorrect model with improvement. System Components Class Diagram. The improved model will accommodate the addition of more types of components, like a scanner, perhaps, a system with more than one monitor or printer, or a replacement component on the shelf that doesn't belong to any system right now. But UML allows us to show the association in a more semantically correct way. In the better model with UML aggregation, System Components Class Diagram, the system is an aggregation of components. In UML, aggregation is shown by an open diamond on the end of the association line that points to the parent aggregated class. There is an implied multiplicity on this end of 0, 1, with multiplicity of the other end shown in the diagram as usual. To describe this association, we would say that each system is composed of one or more components, and each component is part of 0 or 1 system. Since the component can exist by itself in this model without being part of a system, the system name can't be part of its PK. We'll use the only candidate key, type, MFGR, model, SN, as PK, since this class is not a parent. The system name, just an FK here, will be filled in if this component is installed as part of a system. It will be null otherwise. Now let's talk about System Components Relation Scheme. In UML, there is a stronger form of aggregation that is called composition. The notation is similar, using a filled-in diamond instead of an open one. In composition, component instances cannot exist on their own without a parent. They are created with or after the parent, and they are deleted if the parent is deleted. The potential of the internet to consolidate and manipulate information has a new application in data aggregation, also known as screen scraping. The internet gives users the opportunity to consolidate their usernames and passwords, or PINs. Such consolidation enables consumers to access a wide variety of PIN-protected websites containing personal information by using one master PIN on a single website. Online account providers include financial institutions, stockbrokers, airline and frequent flyer and other reward programs, and email accounts. Data aggregators can gather account or other information from designated websites by using account holders' PINs and then making the user's account information available to them at a single website operated by the aggregator at an account holder's request. Aggregation services may be offered on a standalone basis or in conjunction with other financial services such as portfolio tracking and bill payment provided by a specialized website, or as an additional service to augment the online presence of an enterprise established beyond the virtual world. Many established companies with an internet presence appear to recognize the value of offering an aggregation service to enhance other web-based services and attract visitors. Offering a data aggregation service to a website may be attractive because of the potential that it will frequently draw local business data aggregation. When it comes to compiling location information on local businesses, there are several major data aggregators that collect information, such as the business name, address, phone number, website, description, and hours of operation. They then validate this information using various validation methods. Once the business information has been verified to be accurate, the data aggregators make it available to publishers like Google and Yelp. When Yelp, for example, goes to update their Yelp listings, they will pull data from these local data aggregators. Publishers take local business data from different sources and compare it to what they currently have in their database. They then update their database with what information they deem accurate. Financial institutions are concerned about the possibility of liability arising from data aggregation activities, potential security problems, infringement on intellectual property rights, and the possibility of diminishing traffic to the institution's website. The aggregator and financial institution may agree on a data feed arrangement activated on the customer's request, using an Open Financial Exchange or OFX standard to request and deliver information to the site selected by the customer as the place from which they will view their account data. Agreements provide an opportunity for institutions to negotiate to protect their customers' interests and offer aggregators the opportunity to provide a robust service. Aggregators who agree with information providers to extract data without using an OFX standard may reach a lower level of consensual relationship. Therefore, screen scraping may be used to obtain account data. But for business or other reasons, the aggregator may decide to obtain prior consent and negotiate the terms on which customer data is made available. Screen scraping without consent by the content provider has the advantage of allowing subscribers to view almost any and all accounts they happen to have opened anywhere on the internet through one website. Over time, the transfer of large amounts of account data from the account provider to the aggregator's server could develop into a comprehensive profile of a user, detailing their banking and credit card transactions, balances, securities transactions and portfolios, travel history, and preferences. As the sensitivity to data protection considerations grow, it is likely there will be a considerable focus on the extent to which data aggregators may seek to use this data either for their own purposes or to share it on some basis with the operator of a website, on which there are two primary processes: 1. Transaction management, and 2. Concurrency control in database management systems. Transaction management, or TM, handles all transactions properly in DBMS. Database transactions are the events or activities such as series of data read or write operations on data objects stored in database system. Larson, Blanes, Jaconu, Friedman, Patel, and Zwilling, 2011. Concurrency control, or CC, is a process to ensure that data is updated correctly and appropriately when multiple transactions are concurrently executed in DBMS. Connolly and Begg, 2015. In general, concurrency control is an essential part of TM. It is a mechanism for correctness when two or more database transactions that access the same data or data set are executed concurrently with time overlap. According to wikipedia.org, if multiple transactions are executed serially or sequentially, data is consistent in a database. However, if concurrent transactions with interleaving operations are executed, some unexpected data and inconsistent result may occur. Data interference is usually caused by a write operation among transactions on the same set of data in DBMS. For example, the lost update problem may occur when a second transaction writes a second value of a data content on top of the first value written by a first concurrent transaction. Other problems, such as the dirty read problem, the incorrect summary problem, are also identified in the Connolly and Beggs textbook. There are two main kinds of concurrency control mechanisms: the pessimistic or conservative concurrency control and the optimistic concurrency control. The pessimistic concurrency control delays the transactions if they conflict with other transactions at some time in the future by locking or a timestamping technique. According to Kung and Robinson, 1981, the optimistic concurrency control that assumes that the conflict is rare allows concurrent transactions to proceed without imposing delays to ensure serializability, then check conflict only at the end when a transaction commits. Notice that there is another mechanism, semi-optimistic technique, which uses lock operations in some situations if they may violate some rules, and does not lock in other circumstances. Both pessimistic and optimistic concurrency control mechanisms provide different performance. Example, the different average transaction completion rates or throughput, depending on transaction types mix, computing level of parallelism, and other events. According to Vallejo, Sanyal, Harris, Vallejo, Bevide, Unsal, Valero, 2011, there is a trade-off between the concurrency control techniques. Their pros and cons are shown as follows. For pessimistic concurrency control, the strength is guarantee that all transactions can be executed correctly. Data is properly consistent by either rolling back to the previous state, abort operation, or new content, commit operation, when the transaction conflict is cleared. Database is relatively stable and reliable. Its weakness is transactions are slow due to the delay by locking or timestamping event. Runtime is longer. Transaction latency increases significantly. Throughput, or the amount of work, example read, write, update, rollback operations, etc., is reduced. For optimistic concurrency control, the strength is transactions are executed more efficiently. Data content is relatively safe. Throughput is much higher. Its weakness is there is a risk of data interference among concurrent transactions, since transactions conflict may occur during execution. In this case, data is no longer correct. Database may have some hidden errors with inconsistent data. Even conflict check is performed at the end of transactions. Transactions may be in deadlock that causes the system to hang. Many users often encounter the data interference issues in database management systems in stock markets. The simple example addresses the inconsistent data issue as shown as follows. Multiple analysts or investors from Fidelity Investments, LLC, access a client's fund in a database for stock trading from either Dow, bonds, or mutual funds. Both analysts A, B perform some transactions to transfer some amount of money to buy stocks from different funds for their daily works. In this scenario, the nested transaction is used in database. At scheduled step T7, a transaction manager faces inconsistent data. That is $800 or $1,000 in the client's balance. The operating system can execute either thread A for a balanced result of 1000 or thread B for a balanced result of 800. Either case, the balanced content is incorrect. For pessimistic technique, the transaction B may be delayed for a long time or in a deadlock. For optimistic technique, it goes through with incorrect data in the database. Furthermore, the micro-execution of the software Java Database Connectivity, or JDBC, is an application programming interface, or API, for the programming language Java, which defines how a client may access a database. It is Java-based data access technology and used for Java database connectivity. It is part of the Java Standard Edition platform from Oracle Corporation. It provides methods to query and update data in a database, and is oriented towards relational databases. A JDBC to ODBC bridge enables connections to any ODBC accessible data source in the Java Virtual Machine, or JVM host environment. Sun Microsystems released JDBC as part of Java Development Kit, or JDK 1.1, on February 19, 1997. Since then, it has been part of the Java Platform Standard Edition, or Java SE. The JDBC classes are contained in the Java package java.sql and javax.sql. Starting with version 3.1, JDBC has been developed under the Java community process. JSR 54 specifies JDBC 3.0, included in J2SE 1.4, JSR 114 specifies the JDBC Rosette editions, and JSR 221 is the specification of JDBC 4.0, included in Java SE 6. JDBC 4.1 is specified by a maintenance release 1 of JSR 221 and is included in Java SE 7. JDBC 4.2 is specified by a maintenance release 2 of JSR 221 and is included in Java SE 8. The latest version, JDBC 4.3, is specified by a maintenance release 3 of JSR 221 and is included in Java SE 9. JDBC allows multiple implementations to exist and be used by the same application. The API provides a mechanism for dynamically loading the correct Java packages and registering them with the JDBC Driver Manager. The Driver Manager is used as a connection factory for creating JDBC connections. JDBC connections support creating and executing statements. These may be update statements, such as SQL's create, insert, update, and delete, or they may be query statements, such as select. Additionally, stored procedures may be invoked through a JDBC connection. JDBC represents statements using one of the following classes. Statement. The statement is sent to the database server each and every time. Prepared statement. The statement is cached and then the execution path is predetermined on the database server, allowing it to be executed multiple times in an efficient manner. Callable statement, used for executing stored procedures on the database. Update statements such as insert, update, and delete return an update count that indicates how many rows were affected in the database. These statements do not return any other information. Query statements return a JDBC row result set. The row result set is used to walk over the result set. Individual columns in a row are retrieved either by name or by column number. There may be any number of rows in the result set. The row result set has metadata that describes the names of the columns and their types. There is an extension to the basic JDBC API, in the javax.sql. JDBC connections are often managed via a connection pool rather than obtained directly from the driver. Host database types, which Java can convert to with a function. When a Java application needs a database connection, one of the driverManager.get connection methods is used to create a JDBC connection. The URL used is dependent upon the particular database and JDBC driver. It will always begin with the JDBC protocol, but the rest is up to the particular vendor. JDBC drivers are client-side adapters installed on the client machine, not on the server, that convert requests from Java programs to a protocol that the DBMS can understand. Commercial and free drivers provide connectivity to most relational database servers. These drivers fall into one of the following types. Type 1, that calls native code to the locally available ODBC driver. Note, in JDBC 4.2, JDBC ODBC bridge has been removed. Type 2, that calls database vendor native library on a client side. This code then talks to database over the network. Type 3, the pure Java driver that talks with the server-side middleware that then talks to the database. Type 4, the pure Java driver that uses database native protocol. Note also a type called an internal JDBC driver, a driver embedded with JRE in Java-enabled SQL databases. It is used for Java stored procedures. This does not fit into the classification scheme above, although it would likely resemble either a Type 2 or Type 4 driver, depending on whether the database itself is implemented in Java or not. An example of this is the KPRB, or Kernel Program Bundled Driver, supplied with Oracle RDBMS. JDBC:default:connection offers a relatively standard way of making such a connection. At least the Oracle database and Apache Derby support it. However, in the case of an internal JDBC driver, the JDBC client actually runs as part of the database being accessed, and so can access data directly rather than through network protocols. Sources. Oracle provides a list of some JDBC drivers and vendors. Simba Technologies ships an SDK for building custom JDBC drivers for any custom or proprietary relational data source. CData Software ships Type 4 JDBC drivers for various applications, databases, and web APIs. RSS Bus Type 4 JDBC drivers for applications, databases, and web services. DataDirect Technologies provides a comprehensive suite of fast Type 4 JDBC drivers for all major databases they advertise as Type 5. IDS Software provides a Type 3 JDBC driver for concurrent access to all major databases. Supported features include result set caching, SSL encryption, custom data source, DB Shield. OpenLink Software ships JDBC drivers for a variety of databases, including bridges to other data access mechanisms, example ODBC, JDBC, which can provide more functionality than the targeted mechanism. JDB Access is a Java persistence library for MySQL and Oracle, which defines major database access operations in an easy, usable API above JDBC. JNet Direct provides a suite of fully Sun J2EE certified high-performance JDBC drivers. JDBCR4 is a service program written by Scott Clement to allow access to JDBC from RPG on the IBM I. HSQLDB is a RDBMS with a JDBC driver and is available under a BSD license. Schema Crawler is an open source API that leverages a database index is a data structure that improves the speed of data retrieval operations on a database table at the cost of additional writes and storage space to maintain the index data structure. An index is a copy of selected columns of data from a table that can be searched very efficiently that also includes a low-level disk block address or direct link to the complete row of data it was copied from. Some databases extend the power of indexing by letting developers create indexes on functions or expressions. For example, an index could be created on upper, last name, which would only store the uppercase versions of the last name field in the index. Another option sometimes supported is the use of partial indices, where index entries are created only for those records that satisfy some conditional expression. A further aspect of flexibility is to permit indexing on user-defined functions, as well as expressions formed from an assortment of built-in functions. A B+ tree is a balanced binary search tree that follows a multi-level index format. The leaf nodes of a B+ tree denote actual data pointers. B+ tree ensures that all leaf nodes remain at the same height, thus balanced. Additionally, the leaf nodes are linked using a linked list. Therefore, a B+ tree can support random access as well as sequential access. As for the structure of B+ tree, every leaf node is at equal distance from the root node. A B+ tree is of the order n, where n is fixed for every B+ tree. Internal nodes. Internal non-leaf nodes contain at least n/2 pointers, except the root node. At most, an internal node can contain n pointers. Leaf nodes. Leaf nodes contain at least n/2 record pointers and n/2 key values. At most, a leaf node can contain n record pointers and n key values. Every leaf node contains one block pointer p to point to next leaf node and forms a linked list. B+ tree insertion. B+ trees are filled from bottom, and each entry is done at the leaf node. If a leaf node overflows, split node into two parts. Partition at I equals n+1/2. First I entries are stored in one node. Rest of the entries, I+1 onwards, are moved to a new node. Ith key is duplicated at the parent of the leaf. If a leaf node overflows, split node into two parts. Partition the node at I equals n+1/2. Entries up to I are kept in one node. Rest of the entries are moved to a new node. B+ tree deletion. B+ tree entries are deleted at the leaf nodes. The target entry is searched and deleted. If it is an internal node, delete and replace with the entry from the left position. After deletion, underflow is tested. If underflow occurs, distribute the entries from the nodes left to it. If distribution is not possible from left, then distribute from the nodes right to it. If distribution is not possible from left or from right, then merge the node. Indexed file organization. An indexed file contains records ordered by a record key. A record key uniquely identifies a record and determines the sequence in which it is accessed with respect to other records. As we have seen already, database consists of tables, views, index, procedures, functions, etc. The tables and views are logical form of viewing the data, but the actual data are stored in the physical memory. Database is a very huge storage mechanism, and it will have lots of data, and hence it will be in physical storage devices. In the physical memory devices, these data cannot be stored as it is. They are converted to binary format. Each memory devices will have many data blocks, each of which will be capable of storing certain amount of data. The data in these blocks will be mapped to store the data in the memory. Any user who wants to view these data or modify these data simply fires SQL query and gets the result on the screen. But any of these queries should give results as fast as possible. But how are these data fetched from the physical memory? Do you think simply storing the data in memory devices give us the better results when we fire queries? Certainly not. How is it stored in the memory, accessing method, query type, etc. makes great effect on getting the results. Hence, organizing the data in the database, and hence in the memory, is one of the important topics to think about. Let's talk about the types of file organization. In a database, we have lots of data. Each data is grouped into related groups called tables. Each table will have lots of related records. Any user will see these records in the form of tables in the screen. But these records are stored as files in the memory. Usually, one file will contain all the records of a table. As we saw above, in order to access the contents of the files, records in the physical memory, it is not that easy. They are not stored as tables there, and our SQL queries will not work. We need some accessing methods. To access these files, we need to store them in a certain order so that it will be easy to fetch the records. It is the same as indexes in the books or catalogs in the library, which helps us to find required topics or books respectively. Storing the files in certain order is called file organization. The main objective of file organization is optimal selection of records, that is, records should be accessed as fast as possible. Any insert, update, or delete transaction on records should be easy, quick, and should not harm any other records. No duplicate records should be induced as a result of insert, update, or delete. Records should be stored efficiently so that cost of storage is minimal. There are various methods of file organization. These methods may be efficient for certain types of access or selection, meanwhile it will turn inefficient for other selections. Hence, it is up to the programmer to decide the best suited file organization method depending on his requirements. Some of the file organizations are sequential file organization, heap file organization, hash or direct file organization, indexed sequential access method, B+tree, A B+tree is an n-ary tree with a variable but often large number of children per node. A B+tree consists of a root, internal nodes, and leaves. The root may be either a leaf or a node with two or more children. A B+tree can be viewed as a B-tree in which each node contains only keys, not key value pairs, and to which an additional level is added at the bottom with linked leaves. The primary value of a B+tree is in storing data for efficient retrieval in a block-oriented storage context, in particular, file systems. This is primarily because, unlike binary search trees, B+trees have very high fan-out, or number of pointers to child nodes in a node, typically on the order of 100 or more, which reduces the number of I/O operations required to find an element in the tree. The riser FS, NSS, XFS, JFS, REFS, and BFS file systems all use this type of tree for metadata indexing. BFS also uses B+trees for storing directories. NTFS uses B+trees for directory and security-related metadata indexing. ext4 uses extent trees, a modified B plus tree data structure, for file extent indexing. Relational database management systems such as IBM DB2, Informix, Microsoft SQL Server, Oracle 8, Sybase ASC, and SQLite support this type of tree for table indices. Key-value database management systems such as CouchDB and Tokyo Cabinet support this type of tree for data access. Indexes are a common way to enhance database performance. An index allows the database server to find and retrieve specific rows much faster than it could do without an index. But indexes also add overhead to the database system as a whole, so they should be used sensibly. PostgreSQL provides several index types: B-tree, hash, gist, spgist, GIN, and BRIN. Each index type uses a different algorithm that is best suited to different types of queries. By default, the createIndex command creates B-tree indexes, which fit the most common situations. B-trees can handle equality and range queries on data that can be sorted into some ordering. In particular, the PostgreSQL Query Planner will consider using a B-tree index whenever an indexed column is involved in a comparison using one of these operators: less than equals to, equals, greater than or equals to, greater than. Constructs equivalent to combinations of these operators, such as between and in, can also be implemented with a B-tree index search. Also, an is null or is not null condition on an index column can be used with a B-tree index. The optimizer can also use a B-tree index for queries involving the pattern matching operators like and tilde. If the pattern is a constant and is anchored to the beginning of the string, for example, call like foo% or call tilde foo, but not call like %bar. However, if your database does not use the clocale, you will need to create the index with a special operator class to support indexing of pattern matching queries. See section 11.9. It is also possible to use B-tree indexes for I like and tilde asterisk, but only if the pattern starts with non-alphabetic characters, that is, characters that are not affected by upper or lowercase conversion. B-tree indexes can also be used to retrieve data in sorted order. This is not always faster than a simple scan and sort, but it is often helpful. Hash indexes can only handle simple equality comparisons. The query planner will consider using a hash index whenever an indexed column is involved in a comparison using the equal sign operator. The following command is used to create a hash index. Gist indexes are not a single kind of index, but rather an infrastructure within which many different indexing strategies can be implemented. Accordingly, the particular operators with which a gist index can be used vary depending on the indexing strategy or the operator class. As an example, the standard distribution of PostgreSQL includes gist operator classes for several two-dimensional geometric data types, which support indexed queries using these operators. Indexes are special lookup tables that the database search engine can use to speed up data retrieval. Simply put, an index is a pointer to data in a table. An index in a database is very similar to an index in the back of a book. For example, if you want to reference all pages in a book that discusses a certain topic, you have to first refer to the index, which lists all topics alphabetically and then refer to one or more specific page numbers. An index helps to speed up select queries and where clauses. However, it slows down data input with update and insert statements. Indexes can be created or dropped with no effect on the data. Creating an index involves the createIndex statement, which allows you to name the index, to specify the table, and which column or columns to index, and to indicate whether the index is in ascending or descending order. Indexes can also be unique, similar to the unique constraint, in that the index prevents duplicate entries in the column or a combination of columns on which there's an index. PostgreSQL provides several index types: B-3, hash, gist, spgist, and GIN. Each index type uses a different algorithm that is best suited to different types of queries. By default, the createIndex command creates B-3 indexes, which fit the most common situations. A single column index is one that is created based on only one table column. A multi-column index is defined on more than one column of a table. The basic syntax is as follows: createIndex index-name. On table-name, column 1, column 2 name. Whether to create a single column index or a multi-column index, take into consideration the columns that you may use very frequently in a query's where clause as filter conditions. Should there be only one column used, a single column index should be the choice. Should there be two or more columns that are frequently used in the where clause as filters, the multi-column index would be the best choice. Unique indexes are used not only for performance, but also for data integrity. A unique index does not allow any duplicate values to be inserted into the table. The basic syntax is as follows: create unique index index-name. On table-name, column name. A partial index is an index built over a subset of a table. The subset is defined by a conditional expression called the predicate of the partial index. The index contains entries only for those table rows that satisfy the predicate. The basic syntax is as follows: createIndex index-name. On table-name, conditional expression. Implicit indexes are indexes that are automatically created by the database server when an object is created. Indexes are automatically created for primary key constraints and unique constraints. Example: the following is an example where we will create an index on company table for salary column. Hash createIndex salary-index on company salary. Now let us list down all the indices available on company table using /d company command. #/d company. This will produce Query Optimizer uses heuristic algorithms to evaluate relational algebra expressions. This involves estimating the cost of a relational algebra expression, transforming one relational algebra expression to an equivalent one, choosing access paths for evaluating the sub-expressions. Query optimizers do not optimize, just try to find reasonably good evaluation strategies. Query evaluation problem. An SQL query is declarative, does not specify a query execution plan. A relational algebra expression is procedural. There is an associated query execution plan. Solution: convert SQL query to an equivalent relational algebra and evaluate it using the associated query execution plan. Equivalence preserving transformations. To transform a relational expression into another equivalent expression, we need transformation rules that preserve equivalence. each transformation rule is provably correct, that is, does preserve equivalence, has a heuristic associated with it. Selection and projection rules break complex selection into simpler ones. Cond 1, Cond 2, R, Cond 1, Cond 2, R break projection into stages. ATTR, R, ATTR, ATTR, R. If ATTR, ATTR commute projection and selection. ATTR, Cond R, Cond ATTR, if ATTR all attributes in Cond. Commutativity and associativity of join, and Cartesian product as special case. Join commutativity, RSSR, used to reduce cost of nested loop evaluation strategies. Smaller relations should be in outer loop. Join associativity, RST, used to reduce the size of intermediate relations in computation of multi-relational join first compute, the join that yields smaller intermediate result. N-way join has Tn, n! Different evaluation plans. Tn is the number of parenthesized expressions. N! Is the number of permutations. Query optimizer cannot look at all plans. Might take longer to find an optimal plan than to compute query brute force. Hence, it does not necessarily produce optimal plan 9. Pushing selections and projections. Cond R, S, R. Cond S, Cond, relates attributes of both R and S. Reduces size of intermediate relations, since rows can be discarded sooner. Cond RS, Cond RS. Cond involves only the attributes of R. Reduces size of intermediate relations, since rows of R are discarded sooner. ATTRS, ATTR, ATTRRS. If attributes R, ATTR, ATTR, attributes R, reduces the size of an operand of product 10. Equivalence. Example, C1, C2, C3, RS. C1, C2, C3, RS. C1, C2, R, C3, S. C2, R, C1, C3, S. Assuming C2 involves only attributes of R, C3 involves only attributes of S, and C1 relates attributes of R and S. The notion of functional dependencies is used to define second and third normal form, and the Boyce-Codd normal form, or BCNF. Functional dependencies are fundamental to the process of normalization. Functional dependency describes the relationship between attributes, like columns in a table. Functional dependency, or FD, is a set of constraints between two attributes in a relation. Functional dependency says that if two tuples have same values for attributes a1, a2, up until an, then those two tuples must have same values for attributes b1, b2, up until bn. Functional dependency is represented by an arrow sign, that is x arrow sign y, where x functionally determines y. The left-hand side attributes determine the values of attributes on the right-hand side. Armstrong's axioms. If F is a set of functional dependencies, then the closure of F, denoted as F+, is the set of all functional dependencies logically implied by F. Armstrong's axioms are a set of rules that, when applied repeatedly, generates a closure of functional dependencies. Reflexive rule. If alpha is a set of attributes and beta is subset of alpha, then alpha holds beta. Augmentation rule. If A arrow sign B holds and Y is attribute set, then AY arrow sign BY also holds. That is, adding attributes and dependencies does not change the basic dependencies. Transitivity rule. Same as transitive rule in algebra. If A arrow sign B holds and B arrow sign C holds, then A arrow sign C also holds. A arrow sign B is called as a functionally that determines B. Trivial functional dependency. Trivial. If a functional dependency FD x arrow sign y holds, where y is a subset of x, then it is called a trivial FD. Trivial FDs always hold. Non-trivial. If an FD x arrow sign y holds, where y is not a subset of x, then it is called a non-trivial FD. Completely non-trivial. If an FD x arrow sign y holds, where x intersect y equals phi, it is said to be a completely non-trivial FD. Normalization. If a database design is not perfect, it may contain anomalies, which are like a bad dream for any database administrator. Managing a database with anomalies is next to impossible. Update anomalies. If data items are scattered and are not linked to each other properly, then it could lead to strange situations. For example, when we try to update one data item, having its copies scattered over several places, a few instances get updated properly, while a few others are left with old values. Such instances leave the database The Systems Development Life Cycle, or SDLC, also referred to as the Application Development Life Cycle, is a term used in systems engineering, information systems, and software engineering to describe a process for planning, creating, testing, and deploying an information system. The Systems Development Life Cycle concept applies to a range of hardware and software configurations, as a system can be composed of hardware only, software only, or a combination of both. Preliminary analysis. The objective of Phase 1 is to conduct a preliminary analysis, propose alternative solutions, describe costs and benefits, and submit a preliminary plan with recommendations. Conduct the preliminary analysis. In this step, you need to find out the organization's objectives and the nature and scope of the problem under study. Even if a problem refers only to a small segment of the organization itself, you need to find out what the objectives of the organization itself are. Then you need to see how the problem being studied fits in with them. Propose alternative solutions. In digging into the organization's objectives and specific problems, you may have already covered some solutions. Alternate proposals may come from interviewing employees, clients, suppliers, and/or consultants. You can also study what competitors are doing. With this data, you will have three choices: leave the system as is, improve it, or develop a new system. Systems analysis. Requirements definition. Defines project goals into defined functions and operation of the intended application. It is the process of gathering and interpreting facts, diagnosing problems, and recommending improvements to the system. Analyzes end-user information needs, and also removes any inconsistencies and incompleteness in these requirements. A series of steps followed by the developer are: collection of facts. End-user requirements are obtained through documentation, client interviews, observation, and questionnaires. Scrutiny of the existing system. Identify pros and cons of the current system in place, so as to carry forward the pros and avoid the cons in the new system. Analyzing the proposed system. Solutions to the shortcomings in Step 2 are found, and any specific user proposals are used to prepare the specifications. Systems design describes desired features and operations in detail, including screen layouts, business rules, process diagrams, pseudocode, and other documentation. Development. The real code is written here. Integration and testing brings all the pieces together into a special testing environment, then checks for errors, bugs, and interoperability. Acceptance, installation, deployment. The final stage of initial development, where the software is put into production and runs actual business. Maintenance. During the maintenance stage of the SDLC, the system is assessed to ensure it does not become obsolete. This is also where changes are made to initial software. It involves continuous evaluation of the system in terms of its performance. Evaluation. Some companies do not view this as an official stage of the SDLC, while others consider it to be an extension of the maintenance stage, and may be referred to in some circles as post-implementation review. This is where the system that was developed, as well as the entire process, is evaluated. Some of the questions that need to be answered include: does the newly implemented system meet the initial business requirements and objectives? Is the system reliable and fault-tolerant? Does the system function according to the approved functional requirements? In addition to evaluating the software that was released, it is important to assess the effectiveness of the development process. If there are any aspects of the entire process, or certain stages, that management is not satisfied with, this is the time to improve. Evaluation and assessment is a difficult issue. However, the company must reflect on the process and address weaknesses. Disposal. In this phase, plans are developed for discarding system information, hardware, and software in making the transition to a new system. The purpose here is to properly move, archive, discard, or destroy information, hardware, and software that is being replaced in a manner that prevents A core aspect of software engineering is the subdivision of the development process into a series of phases or steps, each of which focuses on one aspect of the development. The collection of these steps is sometimes referred to as the Software Development Lifecycle, or SDLC. The software product moves through this lifecycle, sometimes repeatedly as it is refined or redeveloped, until it is finally retired from use. Ideally, each phase in the life cycle can be checked for correctness before moving on to the next phase. Software Development Lifecycle Waterfall. Let us start with an overview of the waterfall model, such as you will find in most software engineering textbooks. This waterfall illustrates a general waterfall model that could apply to any computer system development. It shows the process as a strict sequence of steps where the output of one step is the input to the next, and all of one step has to be completed before moving on to the next. We can use the waterfall process as a means of identifying the tasks that are required, together with the input and output for each activity. What is important is the scope of the activities, which can be summarized as follows. Establishing requirements involves consultation with and agreement among stakeholders about what they want from a system, expressed as a statement of requirements. Analysis starts by considering the statement of requirements and finishes by producing a system specification. The specification is a formal representation of what a system should do, expressed in terms that are independent of how it may be realized. Design begins with a system specification, produces design documents, and provides a detailed description of how a system should be constructed. Implementation is the construction of a computer system according to a given design document, and taking into account the environment in which the system will be operating, example, specific hardware or software available for the development. Implementation may be staged, usually with an initial system that can be validated and tested before a final system is released for use. Testing compares the implemented system against the design documents and requirements specification and produces an acceptance report, or more usually a list of errors and bugs that require a review of the analysis, design, and implementation processes to correct. Testing is usually the task that leads to the waterfall model, iterating through the life cycle. Maintenance involves dealing with changes in the requirements or the implementation environment, bug fixing, or porting of the system to new environments. Example, migrating a system from a standalone PC to a Unix workstation or a networked environment. Since maintenance involves the analysis of the changes required, design of a solution, implementation and testing of that solution over the lifetime of a maintained software system, the waterfall lifecycle will be repeatedly revisited. Database lifecycle. We can use the waterfall cycle as the basis for a model of database development that incorporates three assumptions. We can separate the development of a database, that is, specification and creation of a schema, to define data in a database, from the user processes that make use of the database. We can use the three schema architecture as a basis for distinguishing the activities associated with a schema. We can represent the constraints to enforce the semantics of the data once within a database, rather than within every user process that uses the data. The first step is requirements gathering. During this step, the database designers have to interview the customers or database users to understand the proposed system and obtain, including documenting the data and functional requirements. The result of this step is a document that includes the detailed requirements provided by the users. Establishing requirements involves consultation with and agreement among all the users as to what persistent data they want to store, along with an agreement as to the meaning and interpretation of the data elements. The data administrator plays a key role in this process, as they overview the business, legal, and ethical issues within the organization that impact on the data requirements. The data requirements document is used to confirm the understanding of requirements with users, to make sure that it is easily understood. It should not be overly formal or highly encoded. The document should give a concise summary of all users' requirements, not just a collection of individuals' requirements, as the intention is to develop a single shared database. The requirements should not describe how the data is to be processed, but rather what the data items are, what attributes they have, what constraints apply, and the relationships that hold between the data items. Analysis. Data analysis begins with the statement of data requirements and then produces a conceptual data model. The aim of analysis is to obtain a detailed description of the data that will suit user requirements, so that both high and low-level properties of data and their use are dealt with. These include properties such as the possible range of values that can be permitted for attributes. Example, in the school database example, the student course code, course title, and credit points. The conceptual data model provides a shared, formal representation of what is being communicated between clients and developers during database development. It is focused on the data in a database, irrespective of the eventual use of that data in user processes or implementation of the data in specific computer environments. Therefore, a conceptual data model is concerned with the meaning and structure of data, but not with the details affecting how they are implemented. The conceptual data model, then, is a formal representation of what data a database should contain and the constraints the data must satisfy. This should be expressed in terms that are independent of how the model may be implemented. As a result, analysis focuses on the questions. What is required, not how is it achieved? Logical design. Database design starts with a conceptual data model and produces a specification of a logical schema. This will determine the specific type of database system, network, relational, object-oriented, that is required. The relational representation is still independent of any specific DBMS. It is another conceptual data model. We can use a relational representation of the conceptual data model as input to the logical design process. The output of this stage is a detailed relational specification, the logical schema, of all the tables and constraints needed to satisfy the description of the data in the conceptual data model. It is during this design activity that choices are made as to which tables are most appropriate for representing the data in a database. These choices must take into account various design criteria, including, for example, flexibility for change, control of duplication, and how best to represent the constraints. It is the tables defined by the logical schema that determine what data are stored and how they may be manipulated in the database. Database designers familiar with relational databases and SQL might be tempted to go directly to implementation after they have produced a conceptual data model. However, such a direct transformation of the relational representation to SQL tables does not necessarily result in a database that has all the desirable properties: completeness, integrity, flexibility, efficiency, and usability. A good conceptual data model is an essential first step towards a database with these properties, but that does not mean that the direct transformation to SQL tables automatically produces a good database. This first step will accurately represent the tables and constraints needed to satisfy the conceptual data model description, and so will satisfy the completeness and integrity requirements. But it may be inflexible or offer poor usability. The first design is then flexed to improve the quality of the database design. Flexing is a term that is intended to capture the simultaneous ideas of bending something for a different purpose and weakening aspects of it as it is bent. Realizing the design. After the logical design has been created, we need our database to be created according to the definitions we have produced. For an implementation with a relational DBMS, this will probably involve the use of SQL to create tables and constraints that satisfy the logical schema description and the choice of appropriate storage schema, if the DBMS permits that level of control. One way to achieve this is to write the appropriate SQL DDL statements into a file that can be executed by a DBMS, so that there is an independent record, a text file of the SQL statements defining the database. Another method is to work interactively using a database tool like SQL Server Management Studio or Microsoft Access. Whatever mechanism is used to implement the logical schema, the result is that a database with tables and constraints is defined but will contain no data for the user processes. Populating the database. After a database has been created, there are two ways of populating the tables, either from existing data or through the use of the user applications developed for the database. For some tables, there may be existing data from another database or data files. For example, in establishing a database for a hospital, you would expect that there are already some records of all the staff that have to be included in the database. Data might also be brought in from an outside agency. Address lists are frequently brought in from external companies, or produced during a large data entry task, like converting hard copy manual records into computer files can be done by a data entry agency. In such situations, the simplest approach to populate the database is to use the import and export facilities found in the DBMS. Facilities to import and export data in various standard formats are usually available. These functions are also known in some systems as loading and unloading data. Importing enables a file of data to be copied directly into a table. When data are held in a file format that is not appropriate for using the import function, then it is necessary to prepare an application program that reads in the old data, transforms them as necessary, and then inserts them into the database using SQL code specifically produced for that purpose. The transfer of large quantities of existing data into a database is referred to as a bulk load. Bulk loading of data may involve very large quantities of data being loaded, one table at a time, so you may find that there are DBMS facilities to postpone constraint checking until the end of the bulk loading. Guidelines for developing an ER diagram. Note, these are general guidelines that will assist in developing a strong basis for the actual database design, or the logical model. Document all entities discovered during the information gathering stage. Document all attributes that belong to each entity. Select a candidate and primary keys. Ensure that all non-key attributes for each entity are functionally dependent on the primary key. Develop an initial ER diagram and review it with appropriate The entity relationship, or ER data model, has existed for over 35 years. It is well suited to data modeling for use with databases because it is fairly abstract and is easy to discuss and explain. ER models are readily translated to relations. ER models, also called an ER schema, represented by ER diagrams. ER modeling is based on two concepts. Entities, defined as tables that hold specific information, data. Relationships, defined as the associations or interactions between entities. Here's an example of how these two concepts might be combined in an ER data model. Professor Ba, entity, teaches, relationship, the database systems course, entity. For the rest of this chapter, we will use a sample database called the company database to illustrate the concepts of the ER model. This database contains information about employees, departments, and projects. Important points to note include: there are several departments in the company. Each department has a unique identification, a name, location of the office, and a particular employee who manages the department. A department controls a number of projects, each of which has a unique name, a unique number, and a budget. Each employee has a name, identification number, address, salary, and birth date. An employee is assigned to one department, but can join in several projects. We need to record the start date of the employee in each project. We also need to know the direct supervisor of each employee. We want to keep track of the dependents for each employee. Each dependent has a name, birth date, and relationship with the employee. Entity, entity set, and entity type. An entity is an object in the real world with an independent existence that can be differentiated from other objects. An entity might be an object with physical existence, example, a lecturer, a student, a car, or an object with conceptual existence, example, a course, a job, a position. Entities can be classified based on their strength. An entity is considered weak if its tables are existence dependent. That is, it cannot exist without the relationship with another entity. Its primary key is derived from the primary key of the parent entity. The spouse table in the company database is a weak entity because its primary key is dependent on the employee table. Without a corresponding employee record, the spouse record would not exist. An entity is considered strong if it can exist apart from all of its related entities. Kernels are strong entities. A table without a foreign key or a table that contains a foreign key that can contain nulls is a strong entity. Another term to know is entity type, which defines a collection of similar entities. An entity set is a collection of entities of an entity type at a particular point of time. In an entity relationship diagram or ERD, an entity type is represented by a name in a box. Existence dependency. An entity's existence is dependent on the existence of the related entity. It is existence dependent if it has a mandatory foreign key, that is, a foreign key attribute that cannot be null. For example, in the company database, a spouse entity is existence dependent on the employee entity. Kinds of entities. You should also be familiar with different kinds of entities, including independent entities, dependent entities, and characteristic entities. These are described as follows. Independent entities, also referred to as kernels, are the backbone of the database. They are what other tables are based on. Kernels have the following characteristics. They are the building blocks of a database. The primary key may be simple or composite. The primary key is not a foreign key. They do not depend on another entity for their existence. Dependent entities, also referred to as derived entities, depend on other tables for their meaning. These entities have the following characteristics. Dependent entities are used to connect two kernels together. They are said to be existence dependent on two or more tables. Many relationships become associative tables with at least two foreign keys. They may contain other attributes. The foreign key identifies each associated table. There are three options for the primary key. Use a composite of foreign keys of associated tables if unique. Use a composite of foreign keys and a qualifying column. Create a new simple primary key. Characteristic entities provide more information about another table. These entities have the following characteristics. They represent multi-valued attributes. They describe other entities. They typically have a one-to-many relationship. The foreign key is used to further identify the characterized table. Options for primary key are as follows. Use a composite of foreign key plus a qualifying column. Create a new simple primary key. In the company database, these might include employee, like EID, name, address, age, salary. EID is the simple primary key. Employee phone, EID phone. EID is part of a composite primary key. Here, EID is also a foreign key. Attributes. Each entity is described by a set of attributes. Example, employee equals name, address, birth date, age, salary. Each attribute has a name, and is associated with an entity and a domain of legal values. However, the information about attribute domain is not presented on the ERD. Types of keys. There are several types of keys. These are described as follows. Candidate key. A candidate key is a simple or composite key that is unique and minimal. It is unique because no two rows in a table may have the same value at any time. It is minimal because every column is necessary in order to attain uniqueness. From our company database example, if the entity is employee, EID, first name, last name, SIN, address, phone, birth date, salary, department ID, possible candidate keys are EID, SIN, first name and last name, assuming there is no one else in the company with the same name. Last name and department ID, assuming two people with the same last name don't work in the same department. Composite key. A composite key is composed of two or more attributes, but it must be minimal. Using the example from the candidate key section, possible composite keys are first name and last name, assuming there is no one else in the company with the same name. Last name and department ID, assuming two people with the same last name don't work in the same department. Primary key. The primary key is a candidate key that is selected by the database designer to be used as an identifying mechanism for the whole entity set. It must uniquely identify tuples in a table and not be null. The primary key is indicated in the ER model by underlining the attribute. A candidate key is selected by the designer to uniquely identify tuples in a table. It must not be null. A key is chosen by the database designer to be used as an identifying mechanism for the whole entity set. This is referred to as the primary key. This key is indicated by underlining the attribute in the ER model. In the following example, EID is the primary key. Employee, EID, first name, last name, SIN, address, phone, birth date, salary, department ID. Secondary key. A secondary key is an attribute used strictly for retrieval purposes. Can be composite. For example, phone and last name. Alternate key. Alternate keys are all candidate keys not chosen as the primary key. Foreign key. A foreign key, or FK, is an attribute in a table that references the primary key in another table, or it can be null. Both foreign and primary keys must be of the same data type. Employee, EID, first name, last name, SIN, address, phone, birth date, salary, department ID. Nulls. A null is a special symbol independent of data type, which means either unknown or inapplicable. It does not mean zero or blank. Features of null include no data entry, not permitted in the primary key, should be avoided in other attributes, can represent an unknown attribute value, a known but missing attribute value, a not applicable condition. Can create problems when functions such as count, average, and sum are used. Can create logical Normalization should be part of the database design process. However, it is difficult to separate the normalization process from the ER modeling process, so the two techniques should be used concurrently. Use an entity relation diagram, or ERD, to provide the big picture or macro view of an organization's data requirements and operations. This is created through an iterative process that involves identifying relevant entities, their attributes, and their relationships. Normalization procedure focuses on characteristics of specific entities and represents the microview of entities within the ERD. So, what is normalization? Normalization is the branch of relational theory that provides design insights. It is the process of determining how much redundancy exists in a table. The goals of normalization are to be able to characterize the level of redundancy in a relational schema and provide mechanisms for transforming schemas in order to remove redundancy. Normalization theory draws heavily on the theory of functional dependencies. Normalization theory defines 6 normal forms, or NF. Each normal form involves a set of dependency properties that a schema must satisfy, and each normal form gives guarantees about the presence and/or absence of update anomalies. This means that higher normal forms have less redundancy, and as a result, fewer update problems. Normal forms. All the tables in any database can be in one of the normal forms we will discuss next. Ideally, we only want minimal redundancy for PK to FK. Everything else should be derived from other tables. There are 6 normal forms, but we will only look at the first 4, which are first normal form or 1NF, second normal form or 2NF, third normal form or 3NF, Boyce-Codd normal form or BCNF. BCNF is rarely used. In the first normal form, only single values are permitted at the intersection of each row and column, hence there are no repeating groups. To normalize a relation that contains a repeating group, remove the repeating group and form 2 new relations. The PK of the new relation is a combination of the PK of the original relation, plus an attribute from the newly created relation for unique identification. Process for 1NF. We will use the student grade report table as follows from a school database as our example to explain the process for 1NF. Student grade report. Student number, student name, major, course number, course name, instructor number, instructor name, instructor location, grade. In the student grade report table, the repeating group is the course information. A student can take many courses. Remove the repeating group. In this case, it's the course information for each student. Identify the PK for your new table. The PK must uniquely identify the attribute value, student number, and course number. After removing all the attributes related to the course and student, you are left with the student course table, student course. The student table, student, is now in first normal form with the repeating group removed. Student, student number, student name, major. Student course, student number, course name, instructor number, instructor name, instructor location, grade. How to update 1NF anomalies. Student course, student number, course name, instructor name, instructor location, grade. To add a new course, we need a student. When course information needs to be updated, we may have inconsistencies. To delete a student, we might also delete critical information about a course. Second normal form, 2NF. For the second normal form, the relation must first be in 1NF. The relation is automatically in 2NF if and only if the PK comprises a single attribute. If the relation has a composite PK, then each non-key attribute must be fully dependent on the entire PK and not on a subset of the PK. That is, there must be no partial dependency or augmentation. Process for 2NF. To move 2NF, a table must first be in 1NF. The student table is already in 2NF because it has a single column PK. When examining the student course table, we see that not all the attributes are fully dependent on the PK, specifically all course information. The only attribute that is fully dependent is grade. Identify the new table that contains the course information. Identify the PK for the new table: student, student number, student name, major, course grade, student number, course number, grade, course instructor, course number, course name, instructor number, instructor name, instructor location. How to update 2 and F anomalies. When adding a new instructor, we need a course. Updating course information could lead to inconsistencies for instructor information. Deleting a course may also delete instructor information. Third normal form, 3 and F. To be in third normal form, the relation must be in second normal form. Also, all transitive dependencies must be removed. A non-key attribute may not be functionally dependent on another non-key attribute. Process for 3 and F. Eliminate all dependent attributes in transitive relationships from each of the tables that have a transitive relationship. Create new tables with removed dependency. Check new tables as well as tables modified to make sure that each table has a determinant and that no table contains inappropriate dependencies. See the 4 new tables as follows: student, student number, student name, major, course grade, student number, grade, course, course number, course name, instructor number, instructor, instructor number, instructor name, instructor location. Normalization and database design. During the normalization process of database design, make sure that proposed entities meet required normal form before table structures are created. Many real-world databases have been improperly designed or burdened with anomalies if improperly. One important theory developed for the entity relational model involves the notion of functional dependency, or FD. The aim of studying this is to improve your understanding of relationships among data and to gain enough formalism to assist with practical database design. Like constraints, FDs are drawn from the semantics of the application domain. Essentially, functional dependencies describe how individual attributes are related. FDs are a kind of constraint among attributes within a relation and contribute to a good relational schema design. In this chapter, we will look at the basic theory and definition of functional dependency, the methodology for improving schema designs, also called normalization, relational design, and redundancy. Generally, a good relational database design must capture all of the necessary attributes and associations. The design should do this with a minimal amount of stored information and no redundant data. In database design, redundancy is generally undesirable because it causes problems maintaining consistency after updates. However, redundancy can sometimes lead to performance improvements. For example, when redundancy can be used in place of a join to connect data. A join is used when you need to obtain information based on 2 related tables.